What's yours?
A little video, if I can get it running. It's an older access video on, it was from PBS, show on PBS.
The DVD.
80s, yeah, 70s.
You should bring in some Bill Nye.
So wherever there's a change in current, so here's what you're going to see. And you've already done this with Fleming's left-hand rule and seen how an induced voltage occurs when there's motion of a conductor through a magnetic field. Also, something else happens when the current in a circuit increases or decreases. The time that it's accelerating or decelerating. Just like you're stepping on the pedal to pass somebody, or you're easing off and it's decelerating. So when there's a change in current, this is the thought that you're going to get to next. Not just a flow of current, whatever level that is, 5 amps, 10 amps, whatever. It's when it changes from 5 to 10 or 10 to 5. It's when during the change. So that's what it says here. In any circuit where a change in current takes place, there will be an accompanying change in flux. So the flux around the conductor, if we had one up here with 5 amps, let's say this was 5 amps, and then it went down to 1 amp. Where would the flux be at, like roughly around? Would it increase, like in space, or decrease with 1 amp? Decrease. Okay, so it's reasonable, right? So if it's like down here, and it's only emanating this far, and then between the flux lines is really far after that, you know, it's not concentrated in any way further away from it. But all the amps are causing the flux to be concentrated near the conductor, then that means that it had to change from that to that, right? So it's during that change, what it's like the flux is expanding and collapsing, not completely, but to a different level. So the time when it's expanding and collapsing, it's like the motion on this left-hand rule. Only it's not the conductor that's moving, it's the flux that's moving, which would be the opposite to the whatever the conductor is. So that's I'm just going to start with that. We're going to mull that around a little bit. I'm not going to get too heavy into it today, but just to sort of get that on your brain, it's when there's a change in current. So in a regular circuit, we have an AC circuit. We have 100 volts. 10 ohms. What is the current? 10 what? Oh, ohms. So there you go, 10 amps. How do I change it to another current in this circuit? What would I do? Yeah, I could add another thing, or I could change this out, or maybe it's variable. Maybe it's variable. I could increase and decrease it. That's the only way. Or I could add another branch with a switch. And then say I close this switch. Then what happens? Let's get rid of the variable.
20 amps?
It would be 20 amps. Yeah, because it draws 2 branches. So the resistance is only 5, so I got 20 amps. So it increased from 10 to 20. So what happened to the flux around this conductor during that time? It was at the 10 amp level, and it went to the 20 amp level. So which direction did the flux go?
Outward.
Oh. Oh, again, hit the rim. Hit the rim.
That's not a draw.
Yeah. Is that the right direction?
Yeah, it is.
Because it checked it, right? I don't trust myself. Okay? So if we've done this, here, let's get rid of this one. If this was the 5 amp level and we had this and this, don't yawning, It's contagious. Only if it has a lid.
You need to buy one of those special.
Usually have one hand out, the presentation.
It's right next to the baking.
Okay, so now I'm going to 20 amps. So this is 10 amps flowing there. Now I've just added another circuit. Now it's 20. So I got twice as much current in that wire. So what does the flux do?
Oh.
Right? So something like that, it's whatever. In proportion, it increases, same direction. So what is the direction of the flux expansion? The motion of the flux. Not the direction the flux lines, but the expansion direction comes
Moves away from the conductor.
away from the conductor. Thank you. So what's happened is went from here to here, in every direction away from the conductor. So that's called expanding flux. Just so when you hear the term expanding, this flux is expanding, it means that a current has increased to cause more flux around something. A conductor usually, or a coil of conductor, right? Anyway, so that's the idea of this. So that would be the flux motion. Well, now it says when this voltage, let's see, there will be an accompanying change in flux density. This change in flux, here's the reaction. There we go. Okay. This change in flux will induce enough voltage in the conductor to oppose the change in current causing it. So right during the time when the current is increasing, it's not a good example with this circuit here, so I'm going to get away from this example. I just wanted to show you how would we increase current in a circuit. Get your brain back into electrical again after reading all those code rules. So that's the reason I did that. Okay, so when the flux is going out in this direction, is it also inside the conductor? Question mark?
Can you say the question again?
Does the flux exist inside the copper conductor as well?
Yes.
Yeah.
In fact, it's probably most concentrated inside the conductor. It's like those rings are like, except for the very center, right? Most concentrated. So did they not also expand out of the center of the conductor? Go like that. Oh yeah, it's just because I don't have this chocolate. Anyway, sorry. Saw a squirrel. So it's expanded out of there. Okay, so what is the direction that the flux is cutting the conductor? Is it, I'll just put the little arrows in here. It also, within the conductor, it has expanded in the conductor as well as outside the conductor. So what's happened here, I'll redraw that portion. We'll zoom in, see map inset, okay, right here, right? See Vancouver map inset. And so the flux is doing this inside the conductor. It's also outside the conductor. So if the flux, I'll try this, flux is expanding that direction. That's the flux. Which direction is the conductor moving? If I cut this conductor in half, let's just look at the one side, what's happening in that direction only, to the left. Which way is the conductor moving, even if it's not moving? It would be like as if the conductor was moving. Which way? No. You're not getting it. You're not getting it. Okay. So if we look at what's happening here, if the water is flowing is the water flowing that way, or is the ground moving this way? It's kind of my idea. Or am I walking this way, or is the ground actually just moving underneath me when I walk and I'm standing still? Right? So that's my point of reference. That's all I'm getting at. Right? So if the flux is, the green here is the flux. If the flux is going that way, it's like the conductor is moving that way.
Yeah.
It's opposite. That's the flux. The stationary conductor that's hopefully not moving, I don't want the wires moving around, right? Would be like it's going that way. So that is the thrust on the left-hand rule is the conductor's the relative motion of the conductor. So it's relative to the magnetic field, even though the conductor didn't actually do the movement. Something moved through it, so it's like it moved through the magnetic field, right? Anyway, so that's my point. So what happens then is which direction, if this is the direction of the current in the conductor, Lenz's law says that it has to oppose the change that caused it, the flux that caused the change. So let's see, does that work? Let's try it out with the left-hand rule. Everybody put up the left hand. Hands up. No. Yeah. The other left hand. Yeah, so anyway, so let's see. Motion of conductor, I'd say if the flux is going that way, then the motion is that way. Which direction are the lines of flux going right at that point? Well, they were going counterclockwise. So right at that point, weren't the flux lines actually the direction of the field? You could say the direction of the field. This is flux motion or expansion. This is flux direction, the field, the forefinger, right? So, doon, doon, oh. So the center finger is pointing at you, which means what? Direction of the current flow. Opposes the current that caused the flux that caused all that to begin with. So it's opposing the increase in current this way, there's something opposing it. In every conductor, this happens. So whenever, and think about AC. We'll get there just yet, but is it changing, increasing and decreasing all the time? All the time, the flux is expanding and collapsing and then changing direction, expanding and collapsing, and it's always doing that. It's constant, expanding, collapsing. So there's always relative motion between a magnetic field and the conductor. But in what piece of wire, it's not a huge deal. It's called self-induction. So in here it says the process by which this takes place is referred to as self-induction, and they only say that because it's just a wire, just a conductor. And it doesn't really have much effect other than it limits the current a little bit. It's really what it does every time there's a change. So it doesn't immediately go from 5 amps to 10 amps. It would block that change, and then it would increase to 10 a little more gradually. So there's a limitation there. Newton's third law of motion states. Anybody? For every action,
There's equal and opposite reaction.
equal and opposite reaction. Okay, so anyway, equal and opposite, we'll get into that later. But okay, so just think about that. And then here it is here. And they explain exactly what I explained. And use Fleming's left-hand rule to figure out that, yeah, it actually would oppose that current direction. There'd be a different current going this way in the wire. The two would cancel each other out, which would really mean there'd be less current going that way than there was before. That's really what it is. So subtract a little bit of it off. All right. Lenz's law, and here it is here. Just highlight that in your book. The direction of the induced EMF must be such. What does it say?
Be such that any current resulting from it will develop a flux that tends to oppose any change in the original flux.
Right. And we proved it, at least on the board. No, not got a video on it, but okay. What I want you guys to do, I'm going to give you a review handout on level 3. Level 1, D3, and not level 3. Not yet. Okay. It says the magnitude, remember VLV?
Yeah.
And V was really the speed of the conductor. Well, it's how fast does this change happen, right? How fast does it increase? It's going to affect how much induced voltage there is. It's all to do with this formula, and this is the induced voltage. It's also called the generated voltage, right? It's also called the instantaneous voltage. Sometimes we call it EG. When it comes to an alternator or a generator, we call it EG, E-generated, but really just E, small e, would be fine. And everyone understands what that is, at least if you write it. Okay, then it gets into the Henry. Okay, there's a pub called the Henry, so you should remember the unit of inductance. What the heck is inductance, first of all? Is the Henry. And I wouldn't worry too much about this. I don't like this definition here. All that is a mathematical statement. It's not really a definition. But it's true. It's just not a good one. Okay, so this isn't the one I want you to remember. But the formula would give you this if you just had a formula for it, right? Electric circuit has an inductance of 1 Henry, right? When a current changing at the rate of 1 amp per second induces a voltage of 1 volt into that circuit. 1 amp per second. So your car, again, if you drive, everyone drive?
Well, according to my mom, I drive.
Even if you don't, somebody's accelerating, right? So they increase the speed. So if you go from 0 to 60K, because you want to obey the speed limit, right? 0 to 60 kilometers per hour. Okay, so I start at 0, and now I'm at 60, right? And if I just let's do a sort of graph over time, and say, okay. So I'm at 60 now. Did I go instantly to 60?
No.
No. It's, I mean, depending on what you drive, faster to 60, the acceleration could be better. It could be an aluminum body, it could be a powerful motor, you could have really good tire traction, the high day, you know, like all these factors, right?
Wind behind you?
What's this? Wind, okay, good. Okay, got that. Okay, so we're at 60, but let's say it took a little time and we'd say, okay, when I get to 60, I have to be able to stay at 60. So do you think I'm going to have to sort of make a curve out of this and say that I'm not going to do this and then this, right? That's kind of hard to maintain. So I'm going to gradually increase and then maybe taper it off, and now I'm at 60. So if I could maintain this is a constant speed, right? So constant speed. What is constant acceleration? Let's change this. Let's change this to meters per second, which is really just a different derivative of kilometers per hour, right? Okay, so let's say we're going 60 meters per second. What would it be if I wanted to do a constant rate of acceleration of 1 meter per second per second? Like keep changing, adding a meter per second every second. That's basically what you're doing. You go faster and faster and faster and faster, right?
You need a line, it's a straight line.
Straight line?
Yeah.
Opposite curve.
Let's like do a 45 line, right?
Yeah.
So that would be constant acceleration. I think you're getting into physics today. But it's all really, it's invisible stuff, but it's still physics. It's still physical things that are doing stuff. It's just the layman's way of saying it, right? Okay, so constant acceleration, if I went 1 meter per second, so that means that every second, and let's get rid of these units here, let's put 60 way up there, and I'm going 1 meter per second in a second. I've increased another meter per second, so at 2 seconds I'm actually going how fast? 2 meters per second, and then it just keeps increasing, and I can't stop. So, you know, that shows speed or whatever, the thing just keeps going. Okay, now, so an acceleration is a change. Constant speed is like, if you think of it like current, if the current gets up to the 10 amp level, now we got amps, they are coulombs per second. So 10 amps, is 10 coulombs per second. 20 amps is 20 coulombs per second. So if I continue to increase, what would the flux be doing as well? Adding more flux lines, you could say, right? So amp turns, say in a coil or whatever, if I could create magnetic field, I would be producing a magnetic field, or even just around the wire, it would do the same thing. So at 10 coulombs per second, it's, if I balanced out on the blue curve here, I'd say I'm changing, not as much change, not as much change, not as much change. Zero change. Even though it's 10 amps, there can be no, as long as there's no change, the magnetic field is stable. It's still there, just not moving. So if you can kind of think of something to relate it to, sometimes it helps. I don't know if that acceleration is an easy one, because if the current is changing, it's either accelerating or it's decelerating. But it's not stable, in other words. Right? If it's stable, it means it could be running, it could be 0 amps. It could be 1,000 amps. Whatever it is, doesn't matter. As long as it's not changing, there's no changing field, there's no induced EMF. We call that, because it goes in the opposite direction, you guys know what you call it? Induced EMF in the opposite direction because it opposes the change. What do you call that? Counter EMF. Yeah, or back EMF. Counter EMF are terms for it. All right. This is getting wild now, I know. Okay. Here we go. Here's review.
Funding for this program is provided by Annenberg CDB to advance excellent teaching.
Excellent teaching. This was before K. Heard of this before.
I like the planets. How do they float good?
Who knows if they're actually floating?
What if this is all a dream?
Okay. Other class. Yeah.
In 1820, Hans Christian Ørsted made his great discovery of how to turn electricity into magnetism. And at that point, every scientist in Europe knew that there was another great discovery waiting to be made, and that was how to use magnetism to create electricity. And they also knew that whoever made that discovery would become immortal. And so all of them scurried back to their laboratories and went to work. And then 12 years passed and nothing happened. Now 12 years is a long time. For most of you, 12 years is 2/3 of your lives. It's nearly half of my life. And yet, in all that time, the discovery was not made. Now in science, once you understand something, it's very difficult to remember what it's like not to have understood it. The fact is that during that period, many experiments were done that had the discovery in them in complicated ways that couldn't be understood. But once the discovery was made and reduced to the essence, it's just as simple as it can possibly be. Let me show you what it was. Here I have a simple loop of wire. My job is to make an electric current run around in this loop. The loop is connected to a galvanometer whose output is that point of light on the screen. So if I succeed in making the current run through the loop, that light will move back and forth on the screen. How am I going to make it work? Well, I've got to do it using magnetism. So here I have a bar magnet. To use this bar magnet to make a current run around in this loop, is very easy. All I have to do is to move the loop into the magnet, or for that matter, back out again. That was it. That was the great discovery. Oh yes, and incidentally, one thing more. If I move the loop back and forth like that, then the current runs back and forth and keeps on going. Well, virtually all electric power, one way or another, is generated by that mechanism. In other words, that discovery is the very basis of our electrical civilization. And that's our subject for today.
Without energy, civilizations go nowhere, not even in circles. But with a strong and steady wind and a comparatively simple machine, an endless supply of power can flow just about anywhere, and once it's been converted to electricity, accomplish what the ancients probably never even imagined. These days, it looks easy enough on the surface, but to understand how wind makes electricity, it's necessary to dig a little deeper and to come up with a bit of historical perspective. The Dutch were masters when it came to windmills. Holland had more water and less cultivated land than she needed. So necessity became the mother of invention, and the Dutch became very good at using the windmill to turn the Rhine River Delta into good dry farmland. But by the 1800s, another kind of revolution was in the air, and it was the churning power and glory of steam. For all their majesty, the future belonged not to windmills, but to steam engines fired by the mineral solid called coal. Coal was inexpensive, as steady as a rock, and as convenient as the closest railroad track. So for a while their coal was really cooking. However, in commerce and chemistry alike, few things have ever remained the same for long. And even as coal was gathering steam in the industrialized nations, a new and different element entered the picture. It was called electricity. Nowhere was it more hotly pursued than at the Royal Institution in London. And no one had pursued it more closely than the 18th century's most diligent and intuitive scientist, Michael Faraday. He probed the mysteries of science because, for him, the building blocks of nature had been created with a fundamental unity. And Mr. Faraday believed that the blueprint was to be found within the laws of physics. With that belief, Faraday was motivated to unearth a new link between two of Mother Nature's fundamental forces, magnetism and electricity. His quest began in 1821 with Hans Christian Ørsted's discovery that the flow of an electric current creates a magnetic field. First, Faraday reproduced the experiment, and then in a roundabout way, he took a major step forward. He invented a device that kept twisting as it followed the circular magnetic field created by a current. And from this point on, when people thought of things turning to create power, they no longer thought of windmills and steam engines alone. With this amazing device, an electric current could create physical work. In other words, this was the world's first electric motor. But Faraday's restless mind saw more than circles of magnetic force in Ørsted's discovery. He saw a crucial scientific question. If an electric current could create a magnetic field, could a magnetic field create an electric current? The answer didn't come easily. It took lamp oil and paper, brilliance and tenacity, untold combinations of coils, magnets, and wires. It took more than a decade, which is why biographers note his legendary patience. But in 1831, Michael Faraday had the answer. As he connected a battery to one coil, current flowed briefly in another coil. He found the answer, and in the process he discovered the principle of electromagnetic induction. How does electromagnetic induction really work? In other words, how can a magnetic field drive an electric current around a circuit? Magnetic fields apply forces to electric charges, but only if the charges are in motion. The direction of the force is perpendicular to the velocity and the field, and depends on the sign of the charge, in this case, negative. For example, the charges might be electrons in a piece of wire. Just moving a wire through a magnetic field makes a current try to flow. But the field of a bar magnet can be perpendicular at every point to a circular loop of wire. So, moving the loop creates a force that drives a current all the way around the loop. The current flows one way if the loop moves upward, and the other way if the loop moves downward. Of course, a current also flows if the loop stands still and the magnet moves. One way if the magnet moves downward. The other if the magnet moves upward. In fact, Faraday found that any method of changing the magnetic field through a circuit would make a current flow. For example, he could induce a current by moving a bar magnet relative to a coil. And when Faraday connected a coil to a battery, the sudden increase in the magnetic field induced a surge of current in another coil. Both these ideas can be expressed in terms of magnetic flux.
The total magnetic flux through a surface is the integral of the component of magnetic field perpendicular to each bit of area that makes up the surface. As a loop of wire moves through the field of a bar magnet, the flux through the loop keeps changing. The changing flux causes a current to flow as if it were driven by a voltage. That voltage, called the electromotive force, E, is equal to minus the rate of change of magnetic flux through the loop. That's called Faraday's law of electromagnetic induction.
A generation later, and a continent away, other pioneering geniuses would make the most of Faraday's discovery. Their names were Thomas Edison and Nikola Tesla. Unlike Faraday, however, their primary ambition was to make machines work and to make them pay for themselves. Edison saw a lot of profit in the business of electricity, but if he were to realize it, he'd need to light up the city of New York. That would require a network of very powerful generators. And no matter the engineering shape they take, the principle of every dynamo would come from Faraday's law of electromagnetic induction.
Rotating a loop of wire in a constant magnetic field continually changes the flux through the loop. The resulting voltage and current are sinusoidal, going first one way, then the other.
Using elaborate sliding contacts attached to the rotating coils, Edison was able to compensate for the oscillating voltage, drawing current that always ran in the same direction from his generators. Tesla thought Edison's system of direct current was costly and inefficient, and that alternating current would do the job better. But AC or DC, one question remains. Which way does the induced current flow?
Current flows through a coil of wire whenever the magnetic flux through it is changing. The current flows one way if the flux decreases, and the other way when the flux increases. But the current induced in the wire also creates a flux of its own, whose direction depends on the direction of the current. The flux created by the induced current always opposes the change in the external flux. This rule is known as Lenz's law. The net result of those fields added together is to slow down the rate at which the magnetic flux through any circuit is able to change.
As electric power grew more important, Lenz's law didn't slow down the rate of change of technological progress. And steam engines weren't out of the picture, not by a long shot. Engines fired by both coal and oil continued to turn generators and create the power of electricity. However, the more that coal and oil were taken away and used up, the more obvious it became that the Earth began with a limited amount. And for some, when it came to fossil fuels, the end was already in sight. So the search for alternatives continued. For a time, hydroelectric power flowed with promise. But in the search for a clean, efficient, and abundant source of energy, all the world's rivers together would never provide enough. And by itself, neither would the wind. But along with geothermal and solar power, the wind provides cheap, decentralized energy that can share the load with traditional centralized generating plants. Taking advantage of current technology, these windmills are much more efficient than their Dutch counterparts of a few centuries ago. In any case, whether electric power comes from the wind or the water, from nuclear power or from coal, it's generated using the principle of electromagnetic induction. And the same principle plays a role in any circuit where electricity is used. An electric current in any circuit creates a magnetic field which, whenever it changes, induces a current in the same circuit that opposes the change. This phenomenon is called self-induction. The effect of self-induction is larger than a coil of many turns, called a solenoid, precisely because it loops many times around the changing flux. That's why a solenoid is used as a symbol of self-inductance in an electric circuit, where an inductor may be an element like a resistor or a capacitor.
Current increasing in an inductor causes an opposing electromotive force, according to Faraday's law. And since the flux is proportional to the current that creates it, that electromotive force is equal to minus a constant L times the rate of change of current. L is called the inductance of the circuit element. An inductor opposes and slows down the buildup of current in a circuit, while a resistor may cause the current to decay by dissipating energy.
But beyond such practical concerns, what's the value of Michael Faraday's theory? For starters, unlike a motor, it's not simple and obvious. And unlike any machine, it's not something one can put a price on. In fact, the value of electromagnetic induction is beyond the economics of technology. And that's because Faraday's theory reveals something new about the nature of electric and magnetic fields, and in the process, changes the rules by which nature's game is played. Magnetic fields circulate, but never converge to a point. Electric fields converge to a point, but never circulate. In mathematical language, that means the line integral of an electrostatic field around any closed path is always equal to 0. But when the magnetic flux through a loop changes with time, it creates an electromotive force around the loop. And that electromotive force is due to an electric field whose line integral is not equal to 0. In other words, there is a way to make electric fields circulate after all, and it's accomplished by changing the magnetic flux. When Faraday discovered that a changing magnetic flux could make an electric field circulate, he added something extraordinary to the laws of electricity and magnetism. So, while it's often said that there's nothing new under the sun, the same doesn't apply to electromagnetic induction.
Now I'd like to show you something truly extraordinary. But first, I have to explain to you what it is you're going to see. When we first started discussing electromagnetic induction, this is how I explained to you how it would work. I said, the wire moves through the magnetic field, and because of the motion of the wire, the charges inside have a force on them, and that sets the current into motion. But when we finally formulated Faraday's law, we were describing it in quite a different way. Then we said that the electromotive force is proportional to the rate of change of the total magnetic flux through the circuit. That suggests that the experiment could be done in quite a different way. What we could do is have a solenoid, that is a helical winding, like this, in which the wire goes around and around, and if we pass a current through that, it creates a magnetic field in this direction. Now if I have a loop of wire around the solenoid like that, and connect it to a galvanometer like that, then when I turn the solenoid on, the flux through that loop will increase even though there's never any magnetic field at the position of the wire at all. And according to Faraday's law, the galvanometer should jump. Well, of course, you'll object to that. You'll say the magnetic field at the position of the wire is not really zero, because the magnetic flux that goes through the solenoid really does have to return outside somewhere, and so there's some magnetic field outside. But I can cure that problem by taking the solenoid and making it bend around onto itself into a kind of a donut, or toroid. Here's what the toroid looks like, and it has some windings of metal wire around it. And when a current is passed through those windings, lines of magnetic flux go around through the toroid and close on themselves without ever going outside. So the magnetic flux outside of a toroid is really equal to zero. Now, if I took a loop of wire and ran it through the middle of the donut, and then back around and closed it on a galvanometer, when I turn on the toroid, the galvanometer should jump, even though the magnetic field at the position of the wire is exactly zero. That's what I would like to show you. I have here a toroid. I can turn the toroid on by means of this switch here, and when I turn it on, there'll be magnetic flux inside, but there won't be any magnetic field at all outside. And I can show you that because I still have my loop of wire here connected to the galvanometer. Now you know if there's a magnetic field turned on at the position of this loop of wire, the galvanometer will jump. So I can put the wire right on top of the toroid like that, as close as I'd like to get it. I turn it on with this switch, and you can see that nothing happens. The galvanometer doesn't bud, nothing. When I open the switch or close the switch, absolutely nothing happens. But if I take this wire instead and put it through the donut, the result is completely different. And I can do that just by opening the wire, threading it through the middle of the donut like this, and closing it again. Now, even though there is still no magnetic field at the position of the wire, when I turn the toroid on, the galvanometer will jump. Ready for this? Watch. There it is. And when I turn it off, the same thing will happen again, like that. Now that is the essence of electromagnetic induction. Now there's something else over here that I wanted to show you about electromagnetic induction. It's this pendulum. This is an ordinary pendulum, but it has a piece of copper at the end. And when it swings, the piece of copper swings between the poles of an electromagnet. But the magnet is not turned on right now. If the magnet were turned on, imagine what would happen. The piece of copper would swing into the magnetic field. Because it's swinging into the magnetic field, then by electromagnetic induction, electric currents would be induced to run around in the copper. And whenever currents run around in a piece of metal, that causes heating. And so there would be heating, and that means that energy is being lost from somewhere. But where does the energy come from? Well, the only place it can come from is the swinging of the pendulum. So the pendulum should actually slow down if I turn on the magnet, which I can do by closing this switch. So here's what I'll do. I'll get the pendulum swinging again, and you sort of get the rhythm of the pendulum swinging back and forth. And then when I close the switch, you'll actually be able to detect that the pendulum slowed down. Okay, so here we go. I'll get it swinging again. Watch it, I'm going to close the switch right now. Watch this. There. You notice that? One more thing I'd like to show you, and that is that not only can electromagnetic induction stop a piece of metal, it can get one going again. Because a piece of metal doesn't like to be in a region of strong changing magnetic field, which I have right here. If I take this ring of aluminum and put it down in the field and turn it on, you should actually be able to see the aluminum jump when I turn the field on. You ready for this? Here it goes. Watch. There. Well, I can't do any better than that, so I'll see you next time.
Well, you do cool stuff like that.
Try. That guy's a rock star.
I want to see metal going.
You caught it. That was mint. Is that it?
Finish up with a couple things because I got some handouts for you guys. And then we can all get on with our skiing home or whatever we're going to do. Nice tube, by the way. That's Okay, so why did the current oppose the original current's direction? Why did it go the other way? What happened to cause it to do that?
The flux setting up.
Flux setting up, okay. Partially. What did it do? When it set up, it
Created a strong.
okay. So what did the current do? What was the current doing? Caused that? The current was increasing, which caused the flux around it to increase. So the flux was doing what? Expanding. Okay, that's the key. Okay, so when that happens, this here, this E, I want you to put in your book, counter EMF. It's actually just plain old E, which is voltage. The voltage that it will oppose is really negative. So that's why this negative is here. Equal negative. So they have a negative there. And the reason is when you do the math part of it, you either get a positive or a negative answer. It will show you whether the voltage aids the situation or counters the situation. Yeah, or opposes. So that negative, we'll leave it in there. And then they go negative L, which is the unit of inductance, and we'll get to that, delta I over delta T. In the video, they had di over dt. They actually had d flux over dt. In little d, sometimes that means delta, or change in, or they'll use the triangle, or change in. So it's really not, I don't really like it like current over time, because you're going to think that it's a steady current. It's how much the current changes over that period of time. It's really delta I over T, or just delta I over delta T, which is the change in time. So that's what the book probably should say. But anyway, you're not, this isn't a unit, this is just change in. You guys know that, right? Change in something. Whether it's an increase, if it's an increase, you make it a positive. If it's a decrease, you make it a negative. So whatever happens. If the time increases, well, the time is always positive, so I guess you don't really need the delta on that one. How long did it take? 5 seconds. You're going to put -5, right? Time only goes one way.
Have they done these tests in space?
Let's go back.
Perhaps.
Because
Okay.
the time moves slower.
So what this means is that the average generated voltage, the generated voltage, or the counter voltage generated in the conductor, or in the inductor, which is just a coil, and we'll get to that, is the amount of inductance it has is the biggest effect. So if I increase the inductance of the circuit, this mysterious quantity called inductance, if I increase the value of inductance, I would increase the generated voltage, or the amount of the voltage will counter in the circuit. This is big in motors, by the way, this counter EMF. Otherwise, you would have like huge currents running through motors. Okay, and then change in current over change in time. So that's current over time. So the average rate of change of current, rate of change of current is a constant value. So because they're saying it's the average rate of change, if this guy, if we ended up from here to here, same point, and we average that guy out to that point, and say, okay, and then they both, and then it leveled off after that, right up to this point, we could say the average of all that was from here to there, straight line. Right? So that's kind of why they say the average rate of change. So this is a constant number. So you can't have that, you can't really say, you know, it's changing this much, this much, and this much, and this much. We'll get to that part of it when we do DC circuits on this. But right now, this formula, you got to go with a constant number. Okay, so that's kind of, I'm sort of relating it to this. The current is directly related to the flux around it. So change of flux, change in flux over time is the same as change in current over time in proportion. One goes up, the other one goes up, and one goes down, the other one goes down, right? That change is the same change. So what the heck is an inductor? Anybody? What are other names? Other names for inductors?
Chokes, coils, reactors.
There we go. Chokes, coils, reactors. Choke's a good name because when the current's increasing, it chokes it. It causes a counter EMF, voltage in opposition to the, so that it tries to stop that current from flowing. It doesn't stop it, but it prevents it or slows it, right? So it's a choke. A coil, because of the way it's made. It's a coil of wire. This is a coil, right? It's actually called a coil, the motor starter. Coil of wire. A lot of inductance in that. What are the factors affecting inductance? Nope. Nope. So what about motor? Is a motor an inductor? They contain windings. They contain coils. So they're inductive loads. Inductive loads, things with inductors in them. They exhibit inductive effects. So when you read through this, air core, oh, where's the core? Right? Right now it's an air core. How do I make this not an air core? Yeah, it goes into this one goes into a contactor, and the core goes around it. The core goes all around this, so that, and through there, so that actually it's fitted. It's fitted to make this fit. So this, because if you burn up the coil, you can change them easier. You can just put the coils in and out. So the core is not an air core, but if you have something that's ferromagnetic and with laminations and the whole bit, then you have a really good permeable, high permeable path for the flux to be set up. So it's going to concentrate better in iron than it will in the air. The air is a bad, sort of medium, pretty bad core. So they say that the air cores are only found in some high frequency applications. Iron core, pretty much everywhere else. Right? So how do you draw an inductor? Symbol for an inductor? So air core would just be simple coil, and the iron core is the two lines over top, indicating that's an iron core. Sometimes it's left out, but just to understand that it's a coil or an inductor. And variable inductor, they just do like they do with the resistor, variable resistor, just put an arrow through it. And how do you change that amount of inductance? Well, they've got a couple things here. Variable inductors, they use them in welding machines, tuners and radio receivers, amplifiers, different ones. So there's some different types. So first of all, I want you to sort of read through that at home, right? Because I can't really talk about it over and over and over, right here. So here are the factors affecting inductance. So this is I'm going to put this in capitals here, not the electromagnetic part. Electromagnetic, what am I going to write next? Induct what? Shun. There's a difference. There's a difference between electromagnetic induction and inductance, magnetic inductance. So if you go to page, the very first page of self-test 6, because we're starting at 6. What does it say there? This is important. Come on. Get it. The very first page?
Yeah.
Isn't it?
Yeah, that's the first page.
Well, I know it's the first page. Am I in the right self-test?
Yeah, you just gotta go down.
Here it is. Write that down as your definition for electromagnetic induction. Or highlight that, memorize that. The process. It is a process. It's something that's happening. It's moving. It's doing something. It's a process. Okay? It's an action-reaction. Right? This is what it is. It's an energy transfer. It's something like that. It's a process of generating a voltage. So like right there, circle that process of generating a voltage by doing what? Okay, so this one here, same one, right? What do you have? Flux, and a conductor, and a speed. What do you have over here? Change in current over change in time is the same as change in flux over change in time would be in the same constant proportion, right? If it's average value. So the change in flux over the change in time where? Through the inductor is speed, flux, and conductor. It's all the same thing. It's just in a different application. Instead of generating a sine wave, this one is reacting to the electricity or the current. It's reacting to the change in current. So that's the process. Now go to page 56. It's way up there. But we're not doing that learning task right now, but we have a better definition. Inductance. So circle the word property. Think of your property. If anyone owns property, or somebody that owns property, it's expensive these days. Is it moving? Hopefully not. Right? We're in a shake zone, or you're on a ravine, and hopefully in any of those situations your property is not moving. Right? That'd be bad. So a property is something like this has the property of inductance, this coil. Right now, there is no process of electromagnetic induction, because I'm not doing anything to it, right? So this has inductance that will affect how much induction will occur, but it's a property. So it's like a resistor. If this was a resistor instead of a ladybug eraser, right? If this was a resistor, it would have a certain amount of resistance. That's the property of a circuit that opposes a change in, property of a circuit that opposes current, not a change in current. Whereas an inductor is a property of a circuit that opposes a change in current. It doesn't oppose current at all, except for whatever resistance is in the wire. It doesn't oppose the current, it opposes a change in current. Whereas this resistor here, work with me on that one, is opposing just current itself. It limits the current. Right? So that's the two differences, but both have properties that will do something if a voltage is applied to them or a change or something is applied. So that's important. Now, what factors affect that? What page were we on at the very end here? This one? Go back to the end of the learning task. What are the factors that affect that inductance? This is a coil. Pretty poorly drawn coil. And that's the back side of the coil. Around the back half of the cord there. So there's a coil of wire, goes in there, out there. Okay? So it's going like this. Best I can do fast. So if the current, here's red. If the current is going through this, in this direction, and out in that direction, then the current is traveling on the front side of this coil, then the magnetic field that's set up is going to be which direction? It's going to be set up, the flux will be traveling in that direction through the core, through the inside of that coil. Right? So if the flux is in that direction, how did I know that? It's this left-hand rule, yeah. The other left-hand rule is that, hey, if the current's flowing in there, and it's going around the back side. Right now, heading down the back side, all those currents are going in that direction before they go to the back side of the coil, right? So if they did that, then using the current through the conductor method, these fluxes would all be going at that point. If you just cut it open right there, if you could do that, but you can't, they'd all be going counterclockwise. So what's happening here is all these are aiding each other. These points here are called flux linkages, because those coil windings, or those little pieces of wire, are so close to each other that they're linking the flux in the same direction with each other. So, well, not really linking, but right here, this is aiding. These two are aiding each other so that it actually becomes something like, eventually something like this, right around the whole thing, right? So those are flux linkages. So they don't, because they're so close together, they just link. So what happens when you have more turns? Well, it's the biggest effect on this. The more turns I put on this, if I double the turns, if you take the number of turns squared, it's the square of those turns that affects the amount of inductance that that thing has, because you're not only increasing the turns, which sets up a line of flux here, line of flux here, line of flux here, line of flux here. You're also doubling the linkages of those fluxes, so it increases to the squared value of the inductance of that coil because of the linkages, because it's put in that pattern. Okay, so the number of turns is squared. Right there. N is number of turns. So you can read it on there. Yeah. The other stuff in there, if this is an air core, well, then that would be a really low number of permeability right there. Permeability would be pretty poor. Let's call it 1 or something. And then A over L, whatever the area, cross-sectional area of the core, length of the core, you remember that? I went over that one day. All the rest of that stuff, oops, what is that? Are the properties of the core. And this is the number of turns. So, if I changed from an air core, and I put inside here iron core, and I made it a better path all the way around so that that flux could return through that same core, then I would say I got 10 times better permeability. What have I done to the inductance? If I increase the permeability of the core by 10 times. So this one goes times 10, this one goes times 10, right? So in proportion. If I increase the area of the core, it also goes up. So I'm going to go double the area of the core, I'm going to double the amount of inductance. If I shorten the length of the core, give the magnetic circuit path a shorter path, and I go times 1/2, let's do a different color actually, times 1/2. That would be like timesing by 2, right, on the other side, because it's divided by the length. But the biggest factor affecting the inductance of the coil, number of turns. If I put 10 times the number of turns, what happens to the inductance? It goes 10 squared on the other side to be equal, so times 100. This is one of those concepts with power that we try to get all ones used to, that when you increase the voltage, you double the voltage, what happens to the power is it's 4 times, right? Anyway, that question. Well, this is similar. So what have we done? We've gone 10 times 10, it's 100, yeah, anyway. Whatever we've done, we can see that the biggest effect is the number of turns. So, So read through that, and then I've got some handouts for you guys, and I think that's probably enough to get into your brain about inductance. But the two things are those two definitions. The property, inductance is a property, and induction, what is it?
Process.
Process, yeah. And